Görüntü bekleniyor herhalde. Bizi bekliyorlar hocam. Görünce atlarsın. Şurada oturuyor. Ama yeah, well, I have exactly the same, but when is your session? I'm not seeing
Değerli hocalarım ve katılımcılar, öncelikle merhaba. Ben Emine Acar, Uludağ Üniversitesi İnşaat Mühendisliği bölümünde doktora yapmaktayım. Yansıda başlığı görünen sunumu sizlere sunacağım bugün. Burada TÜBİTAK tarafından desteklenen ve benim de aynı zamanda bursiyeri olduğum Karadeniz ve Azak Denizi'nin dalga spektrum iklimi başlıklı projemizden çıkma bir çalışma bu. Sunuma İngilizce olarak devam edeceğim. The presentation consists of four main parts. The wind and wave climate is one of the most critical factors in understanding the sea situation and also in the design and planning coastal structures. The wave spectrum describes the random waves generated by the wind. One of the most important determinants of the spectrum is spectral peak energy. You can see here the spectral peak energy point. Wind speed directly affects the shape of the spectrum. Since the climate system is interconnected, the winds affected by the climate change will directly affect the waves generated and spread by the wind. For this reason, this study examines the long-term change in spectral peak energy and the wind speed due to climate change using classical tests and innovative trend methods. In line with this goal, man-candle and innovative trend analysis methods were applied to the annual maximum and mean of 42-year spectral peak energy and wind speed obtained from the wave spectra produced by the Swan wave Hinkens wave model forced with the Era 5 wind field. You can see here our process step. Firstly, we obtained the data sets for spectral peak energy from Swan wave model and for wind speed from Era 5 reanalysis. Then we prepare the data set as annual maximum and annual mean. Then we applied the trend analysis, man-candle trend test and innovative trend analysis, change boxes method. Then we examine the results. Our study area is Black Sea, including the Azov Sea, you can see here. We obtained the spectral peak energy from Swan wave model. Swan is a third generation wave model that developed at the Delft University at Technology that computes random short-chested wind-generated waves in coastal region and inland waters. You can see here the properties of the Swan wave model spectrum. A total of 36 stations over the Black Sea and Azov Seas were selected to perform trend analysis. And wind data we obtained from the Era 5 reanalysis were obtained from the Copernicus Climate Change Service Climate Data Store. Era 5 reanalysis is the fifth generation ACMWF atmospheric reanalysis of the global climate. It provides hourly estimates of the large number of atmospheric, land, and oceanic climate variables. You can see here there are methods, man-candle test and innovative trend analysis change boxes. Man-candle test is non-parametric test and is widely used in the trend analysis studies. We firstly calculated the man-candle test statistic S and connected with this parameter Z value. We examine the increasing or decreasing trend with the critical Z value and the calculated Z value. And here, innovative trend analysis. We divided the data as first half and second half equally. And If the data is below the line here, we say there is a decreasing trend. If the data above the line, this line, we say the parameter is increasing. Innovative trend analysis change boxes method just data divided as high and low value category by petit test. We apply the petit test, find the change point, and we can divide the low category and high category the data. Here we can see the formula of the percentage change for each group. Our results. There is Mann-Kendall trend test results for annual maximum and wind speed and spectral peak energy. Here the wind speed, maximum wind speed and maximum spectral peak energy, mean wind speed and mean spectral peak energy. As we can see, when evaluated holistically with the classical Mann-Kendall, a significant trend could not be detected in almost any station because the confidence level was generally below the 50%. Here you can see there is no trend in here in most of the stations. The upward triangle means the increasing trend, and the downward triangles means increasing trend, by the way. And however, it was noteworthy that only the maximum wind speed showed an increasing trend above the 19% confidence level. Here, innovative trend analysis change boxes result for annual maximum wind speed and spectral peak energy. There is wind speed, maximum wind speed, and maximum spectral peak energy. In this method, a detailed analysis of the change rates was made for low, high, and all categories. Here, there is for low, high, and for all data. The change rate of the wind speeds remained lower than the spectral peak energy. Here, we assess the ETA, the classical ETA, and the ETA change boxes method for annual maximum wind speed and spectral peak energy, a few stations. We can see that this red line, it's represent the in ETA graph. You can see here the outliers point. The outlier points reflect as a red plus sign here. And innovative trend change boxes result for the annual mean wind speed and spectral peak energy here. Lower rates of change were observed in the mean parameters compared to the maximum parameters. Here again, the assessment of the innovative trend analysis and innovative trend analysis change boxes method. It was determined that the spectral peak energy also increased when the wind speed increased in the most stations, especially at high category values. This situation is more clearly seen in the mean parameters here. It draws attention to the fact that the coastal demands may be affected in this region with the increasing trend determined at the stations representing on the Eastern Black Sea. Thank you for listening to me.
Now my voice. Okay. Good morning, Alundra.
Good morning, Professor Kuchak. Can you hear me?
Okay. We are ready to listen to you. Okay.
Okay, you can hear me, I think. Yeah. Thank you, Professor Kuchak, and just let me make. I think you can see my presentation. My name is Ali Umran Kömüşçü. I am working at the Hacı Bayram Veli University in Ankara in the Geography Department. We prepared this presentation with Mehmet Aksoy from Turkish Met Service. It's about analyzing the trends and the periodicities of the Turkish precipitation for the 1975 and 2021 for the 48 years of period. As all of you know, precipitation is a very essential climatic parameter, and it has many implications for different industries and different sectors, particularly agriculture and hydropower production. But as also we know that precipitable parameter both in time and space, so that's why it's very important to know the trends and the variability of the precipitation. So that especially the decision makers and the managers, they can plan their projects and their risk based on the precipitation information. So one of the main reasons that motivated us to do this study was that the precipitation is a highly irregular and highly season variable, and it has a lot of applications for different sectors. So it's very important to know its change over time. So in this study, what we did was to analyze the long-term trends and the periodicity of the monthly and the seasonal, both wet and dry precipitation. And for that purpose, we used around 213 stations for the 1975-2021 period. There were a number of research questions we tried to answer for in this study. One of them is that what is the direction of the monthly and seasonal precipitation in Turkey in the last 4 decades? Second question was, if there's a significant trend, what is the amplitude of the change in this series? Third question was, what are the main trend change points in the precipitation series? And finally, if there's any periodic or cyclic component in the season and the annual precipitation, and how do they vary for different time scales? So basically the methodology we applied in this study was just the previous speaker already mentioned about Mann-Kendall. So at the basic level, we used the least square regression and the Mann-Kendall for the trend test. Then to examine the magnitude of the trends, we used the sense slope estimator. In order to identify the trend change points, we used the sequential Mann-Kendall test. And finally, we used the Morlet wavelet analysis to identify if there's any cyclic component in the precipitation series. Of course, before using this data set in another study, you have to run some quality control and homogeneity tests, and that's what we did in this study. And initially, in fact, we started with the 343 stations, but after we run quality control and homogeneity test, we had to reduce the number of stations to 213, because around 30 stations were excluded. Either they were inhomogeneous or they lacked the complete data to be used in this study. Here you see the spatial distribution of the stations that we used in this study. The red dots, they passed the test, quality control test and homogeneity test, and the blue colored dots, they failed. For some reason, either they had the incomplete data or they were inhomogeneous. Okay, before we run our analysis, we had to set the period as wet and dry. So we looked at the annual mean precipitation cycle, And as you see here, the monthly variation of the precipitation in Turkey and for each geographic region as well. So based on this information, we set the wet period from October to May and the dry period from June to September. So let's look at the basic level, how the trends are changing. As you see on the left side, the annual trends. And what we notice in the annual trends, usually except the Asian region and the Black Sea region, the trends are downward in annual precipitation in Turkey. On the right side, you see the wet period and the dry period. And the wet period also, the trends in the wet period very similar to annual trends. So it's again, Turkey and in general, and also all the other regions except the Black Sea and the Asian region, we can exclude them because the trends were upward slightly in those regions, but the other regions, the trend was downward. And interestingly, in the dry period, in all the regions, the trend was upward. So during the dry period, we can say that the precipitation in Turkey is increasing in general and in all the regions as well. Here you see a table is showing us the annual precipitation means and their trend for different periods for Turkey and the different geographic regions. Just to make it simple for you to understand, maybe we can look at the last period, which is 2012 and 2021 period, this last 10-year period. As you see, the trend is negative in all the regions. In the last 10 years, that means the precipitation are decreasing in Turkey and in all the geographic regions. The last column is for the whole period, 1975-2021. Again, as you see, it is also to some extent reflect the graphs that I showed you earlier. As you see, the Turkey in general and also the most other geographic regions except the Asian and the Black Sea, the precipitation are on the downward side. Here you see the spatial distribution of the precipitation trends. So how do they vary from region to region? Whether if these trends are significant or not. As you see here, the annual and the wet season precipitation almost they portray the similar spatial distribution. And as you see on the Black Sea coast, usually the trend is upward, but in the central and the eastern parts are usually both in the annual and the wet season, the trends are downward. In the dry season, as you see, it is upward trends, except in the eastern part of Turkey. But also the increases are significant even in the dry season in the western part of Turkey and also in the eastern, some parts of the Black Sea region. Here you see the percentage of the stations with the upward and downward trends for Turkey and its geographic regions. As you see, like in general, now 5.2% of all the stations were significantly positive. I mean, the trend was upward in Turkey, and 4.2% of this was located in the Black Sea region. Again, from the significant negative part, 10.8% of all the stations were negatively significant, and 3.8% of those were in the central Anatolian region. So Black Sea is marked with the upward trend among all the regions, and the central Anatolian region is marked with the downward trend in our analysis. Here you see the distribution of the monthly precipitation trends for each month. I will not go over all of the months, but just want to draw your attention to 2-3 months here. One of them is the April. You see, especially in the central part of Turkey, the trend is downward in April. And similarly, in November, most of the trends is downward. And these are, I think, very critical in terms of water resources and agriculture, especially in the central part of Turkey. Usually what we noticed, the trend was downward during the summer months, except the July. And in the winter months, the trends were usually upward. So this is one conclusion we can get from these maps. Here you see again for each month the percentage of the stations with upward or downward trends. And as you see, like in March and August, like as you saw on the maps, March and August are characterized with the increase in the temperatures. In the precipitation. On the other hand, the April and the November were marked with the downward trends. So these are the 4 months that we should pay our attention. So the regarding the precipitation trends. Here you see the trend change points of the annual precipitation over Turkey. Basically, just to understand in a simple way, except the Asian region, we did not notice that whether these trends were trend change points were very significant. As you see, the Asian region is showing a consistently upward trend starting from 1975. And the trend change points in the most of the regions, they were not constant. I mean, they change from year to year. And so usually whether the trend change points and the ending of these trends were not constant in each region. Here you see the spatial distribution of the sand slope values for the annual wet season and dry season. So this is actually telling us, okay, we identified the trend, but what is the magnitude of the trend? How big it is? So basically, you see the change in the precipitation per year. In the annual map, you see, especially along the Black Sea coast, most of the precipitation is increasing at a rate of like more than 4 millimeters per year. Same is almost true for the wet season. And in the dry season, you see it's all upward trend, as we saw in the graphs previously. So there's no almost downward trend. And the areas where the precipitation are decreasing are located in the Mediterranean coastal area and also scattered around southeastern Anatolia and parts of the eastern Anatolia, as you see. And this is the monthly distribution of the values. I mean, the magnitude of the trends for each month. As you see again here, April is, you can see the trend is downward and almost up to like 2 millimeters per month. There's a decrease in the April values. And the month with upward trend, you can see like September and March are also, especially you can see the trend is upward. And also the increase, especially in the Eastern Black Sea area, the monthly precipitation increase goes up to almost 3.5 millimeters. Okay, so this is the trend part. And the last part of this study was about identifying if there's any periodicity with the precipitation series. Here you see the monthly rainfall. This is where we applied the wavelet transform methodology. Here you see, this is the graph in the middle, where you see there's a continuous band of what we call the power spectrum here. And it is, you see this peak here, it's showing us the periodicity of the monthly values, monthly precipitation data. And it varies from 8 to 16 month, average is the 12th month. So there's a 1 year, what we can say, a dominant periodicity in the monthly value. So 1 year, 12 months means in this case, you have both wet and dry periods, like 6 month wet and almost like 6 month dry to some extent, but it can vary, not fixed. But we can see in this case the seasonality of the monthly values in the monthly power spectrum. In the graph in the down, with the D, this is the scaled average power over the 8 to 12 month part, and this is just telling us the periods which are wet and dry. And usually you see the period which is wet is starting from almost like 1977 up to 82, 83. So the the periods above this dashed line are usually the wet and below are dry. So actually what we can see, the usually dry and the wet periods, they follow each other. And but what we noticed as we come toward like end of, they frequently occur, but the duration becomes less, especially toward the end of the toward the current period. So this is the monthly values, the regional values of the power spectrum. Of course, the regional values did not show very continuous power spectrum. So that means still the dominant periodicity is the 1 year, but it's not very continuous. So there are some cutoffs in the power spectrum in most of the regions, except maybe you can say the southeastern Anatolia to some extent, and also the Mediterranean region showed a little bit more continuous values. But the others, there were a lot of cutoffs. So I mean, there's 1 year variability, but it's not very, very strong in those regions. This is the wet season power spectrum, and the wet season power spectrum, as you see, again, there is a from, we can say 6 to 4 to 10 band month band variability. But as you see, again, the power is not very continuous power spectrum. So here you can see that it makes one peak here and another smaller peaks, but these are not very substantial peaks. And this is the one which is more dominant. So it's around eight months of seasonality for the wet season precipitation over Turkey, we can argue. And this is the regional distribution of the power spectrum. Again, as you see, the spectrum powers are not very continuous. There are a lot of cutoffs, and also the peaks usually 8 months is dominant, but also there are some sub periods, but these are statistically not very significant, as you see. Except Eastern Anatolia is and the Southeastern Anatolia is a little bit showing different peaks. Like here, you can see in Eastern Anatolia, 8 months is not the dominant one, and so there are smaller sub periods which are more dominant. And there's one here around 64 months of it's almost like 5.5 year periodicity for the wet period for the Eastern Anatolia. This is a little bit strange. For the dry season, we identified 2 peaks again for the as the power spectrum as the periodicity, and the 4 month is one of them, and there is another one around 24 months, but this is toward the end of the spectrum. So it's not very strong, but you can say as a secondary maybe peak. But the main peak is around 4 and 6 months for the dry season as well. This is also the regional distribution of the power spectrums for Turkey. And again, here you see the power spectrum have a lot of cutoffs, so it's not very continuous. And interestingly here, although we said the 4 month is the 4 to 6 month is the dominant variability, but toward the end of the spectrum here you see in almost on all the regions there is a secondary peak. So around, we can say between 2005 and 2015 there is an additional peak is appearing almost in all the regions. So this is also we can say so for the regional power spectrums do not match exactly the general peak, and so from region to region, so we can see in the dry season variability might change. Basically, the difference between I mean in terms of interpretation of these peaks, what we can say, as we know, the Turkey is affected by different type of weather systems throughout the year. So that's why the seasonality of the precipitation will not be the same for all the regions. So one part of the country can be affected from the precipitation patterns like during winter, and another part will be in spring and March. So that will affect the peaks of the peak of the variability from region to region. So this is showing us that actually the Turkey is under effect of different weather patterns and different air masses, different atmospheric pressure systems, which are affecting the precipitation conditions throughout the year. This is the last graph on this part is we also did the annual rainfall power spectrum. The others were monthly, wet season, and dry. The annual also is important because in the annual one, so we can connect these the changes in the peaks with some teleconnection patterns, and this is very important. As you see in the annual one, the peak goes to the periodicity is peaking around like 8 years. So there's a main peak is around 8 years. It changes between you can say 6 to 10, but the average is around the 8 years. So usually the 8 year 8 year periodicity, we can if you try to connect or attach some explanation for this peak. As you know, for example, North Atlantic Oscillation also has a similar peak from 6 to 8 years. And also Mediterranean Oscillation we found in another study that has some periodicity around this year period. So what we think is that maybe the 8 year periodicity that we identified with the annual rainfall might be related to both North Atlantic Oscillation and the Mediterranean Oscillation. So these are one important conclusion that we reached from this study. I also listed, if we have time, I will go over the conclusions very quickly, Professor Koçak, if we have time. I have a few more slides if I have time. You can interrupt me if I don't have time. Okay, let me go over them very quickly. The conclusions. So what we reached in this study was mainly a declining trend for the majority of the regional precipitation and the national series as well. 3 regions, Marmara, Black Sea, and the Asian region, were noted with the upward trend in their monthly precipitation. And in the Black Sea, showed the most marked increase in the precipitation. The dry season precipitation usually exhibited increasing trends in all the regions. That's another important conclusion that we reached from this study. As far as when we applied the main candle test, we noticed that the both annual and the wet season, they displayed almost a similar spatial distribution. So we can argue that the wet season precipitation usually control the annual precipitation in Turkey, and this is very important because as you know, most part of the annual precipitation usually fall in the wet season in Turkey. It's almost like 75%. So, and this is also reflected in in our study as well. Most of the fall and spring months are characterized with downward trends, almost from June to September, except July. On the other hand, April and November, we identified that the trends were downward. So, especially in the southeastern and central and eastern parts, the annual decrease in the precipitation reached almost 7.5 millimeter per year. So this is a very noticeable decrease in those three regions. Starting point of the trends and the trend shift points show the very different pattern from region to region. Except the Asian region, none of the series had more than one significant trend change point. Usually the trends, in general, trends change started around mid-90s. But of course, as I said, it varied from region to region as well. And the agency and the Black Sea region, they showed more discernible pattern in terms of the increase or decrease in the precipitation. The one thing also we noticed the eastern and the southeastern Anatolia, yes, they have some downward trends as we noticed from the numbers, but this trend changed toward during the last two decades as compared to some other regions. I have two last slides about the conclusion. Usually the wet season spectrum indicated 6 to 10 month dominant period of variability for as far as the periodicity is concerned. And most also regional wet period graphs, as we noticed, they showed 1 year band as a dominant period of variability. But in the wet period, there are a lot of power reductions. So that means the variability is not very, very strong. And as far as the regional series are concerned, and Central Anatolia region showed 4 to 6 months, and the Eastern and the Southeastern Anatolia showed 5 to 6 years of periodicity. One conclusion we came is that usually the inland regions, like, I mean, the regions which does not have any coast, have periodicity more than 1 year as far as the wet season is concerned, but the coastal regions usually did not exhibit periodicity more than 1 year. So as we go inside, the periodicity is becoming a little bit longer, over 1 year. For the dry season, as we said, usually the periodicity is around 4 to 6 months within the 4 to 6 month band. But there's also one periodicity at the 2 year scale. And so it's not very constant from region to region. And one thing we can add for this dry season variability is that the most of the decrease in the power spectrum was between 1975 and 2005. So the variability during those years were a little bit, I mean, even though we identified 4 to 6 month variability, but for this period, it is a little bit, I mean, the significance of the variability is not very strong. Lastly, annual precipitation, as I said, 8 years of periodicity, and also there is one periodicity, maybe I forgot to mention, as a secondary periodicity from 2 to 4 years. So two different periodicity we identified for the annual series. One is 8 year one, other one is from 2 to 4, so average we can say 3. So as I said in my speech earlier, we can maybe connect 8 year periodicity with the North Atlantic Oscillation and the Mediterranean Oscillation for this for the annual series. So this is actually all this eventually what is telling us. It is telling us that the periodicity of the annual and regional I cannot hear you well. Hocam sizi iyi duyamıyorum. Hocam benim konuşmam bitti. Sorular varsa alabilirim. Yalnız sesiniz gelmiyor hocam. Hocam bana sesiniz hiç gelmiyor. Oldukça kesikli.
Sesimiz geliyor mu?
Şu anda geliyor.
Okay. Dear speaker, can you hear me? Okay. Okay. Okay. Okay. Any question or contribution to this paper? Okay. Such a connection problem. I think it is fixed now. Right? Okay. Any questions? Okay. No. Dear speaker, thank you very much for your presentation. Okay.
Thank you, Mr. Professor Koçak.
Good morning to everybody. In fact, this paper will be presented by Evren Özgür. But unfortunately, he cannot be able to present this study. Okay, I will try to present instead of him. Title of this study is Determination of Critical Temperatures Between Snow and Rain, case study of Marmara region. Okay. What's the motivation behind this study? Okay, let me briefly about this subject. What's the with the study, it is aimed to fill the following research gaps in the literature. Okay, first one is there are no studies on critical temperatures in Turkey. In literature, there is only one study related with the Northern Hemisphere, but this study gives really general information about the critical temperature of Turkey. Okay, the result of the current study will provide necessary information for the Northern Hemisphere and especially for the Southeast Europe. In which there are many studies conducted on the critical temperature. The first one is first study is conducted by Auger in 1974 in the USA. Okay, in the study, Auger found the critical temperature 2.2 degrees centigrade. Okay, following our study, okay, as you can see from this table, okay, many studies have been conducted. Okay. Okay. The definition of critical temperature is the key concept of this study. Okay, what is the critical temperature? How can we define the critical temperature? Exactly. Okay. Critical temperature, definition of critical temperature can be given as a temperature at which both the rain and snow have the same occurrence probability of 50%, called the critical temperature. Okay, light. Okay. From this or this graph illustrates schematically what the critical temperature is. Here, dashed line, okay, shows the occurrence probability of snow, and heavy line, okay, shows the occurrence probability of rain. Okay. The horizontal axis is temperature, vertical axis is the occurrence probability. Okay, you see, okay, minus 2.5 degrees centigrade and up to 6 or 6.5 centigrade. It's low temperature. Okay, snow probability is high. Okay, when we increase temperature, occurrence of the snow probability will begin to decrease. Okay. Contrary to this oscillation, okay, at the low temperature, occurrence of rain probability, okay, will be low. But when temperature increases, the occurrence probability of rain will increase. Critical temperature corresponds to the probability of 0.5. This point is the intersection of these two lines. Okay, this is the about 1.4, okay, and so on, is the critical temperature. This red arrow shows the point of the critical temperature. Okay. You see the station, okay, used in the study about 80 stations were used in the study to calculate or in the calculation of the critical temperature. Okay, data set administered in the study are as follows: precipitation continuation hours, hourly temperature. Okay, the data for the 1997 to 2016 period was used in the calculation of critical temperature. Our relative humidity, which is used in the calculation of dew point temperature, and the data for the 2007 to 2016 period was used in the calculation of critical dew point temperature. In short, we have used okay, our temperature and our relative humidity, okay, besides the precipitation continuation or in the study. Okay, you know, the first equation is the Clausius-Clapeyron equation. By using these two equations, okay, we calculate the dew point temperature, okay. Let me pass quickly the data set and methods used in this study. Of course, it is necessary to analyze the data or to prepare data okay, in order or facilitate the calculation of critical temperature. Okay. Here you see, as for example, for the calculation of critical temperature, this graph is belongs to full calculation period for Bursa meteorology station. Okay. And this arrow shows the critical temperature value calculated for Bursa. And the last two graph is the first and second decades. In other words, we have split the two data sets into two equal parts. Okay. Here, for Bursa, we show the first decade and the corresponding critical temperature. And this is the second decade and corresponding critical temperature. Okay, okay. From these two graphs, okay, we calculated the increase 0.3 degrees centigrade. Mm. In other words, there is a small increase in the critical temperature between 2 degrees. And this is the critical dew point for sun. This is the area distribution of critical temperature across the Turkey, across the whole country. Okay. Due to the limited time, I just want to enter the detail, but you can see from this map, especially southeast part of Anatolia and the north part of Marmara region, and some part in Anatolian, inner Anatolian region. The temperature are low, very low, but the other parts of the country, critical temperatures, they become to increase as shown from this map. And this is the area distribution of critical dew point temperature. Again, as you can see from this map, especially some part of Black Sea and western part of Aegean Sea has a very low dew point temperature. And on the other hand, southeast Anatolia and west part of the Marmara region has a high critical dew point temperature. And we also investigate the relationship between temperature, relative humidity, and the air pressure. Okay. What's the relationship between temperature and these meteorological variables? The first one shows the aeration versus critical temperature. Okay. There is a weak relationship, weak linear relationship, but this linear relationship is not statistically significant. Okay. Okay. Below this, there is critical dew point temperature versus aeration. Again, there is no significant relationship between the variables. And this insignificant relationship are also valid for the remaining meteorological variables, relative humidity, air pressure, and so on. But only there is a significant relationship between critical dew point temperature and relative humidity. Okay, here's the results. Okay, critical temperature vary between 0.5 and 2 degrees centigrade for across the country, for the whole country, and 1.2, 2.2 degrees centigrade for Marmara region. For the whole period, average of the critical temperature for all those countries 1.2 degrees centigrade and 1.6 degrees centigrade for Marmara region. For the first decade, average of the critical temperature is 1.2 and 1.4. For the second decade, average critical temperature is 1.7 and 1.9. And this is the important point. Okay, the increase between the decade, is calculated to be 0.5 degrees centigrade and 0.5 degrees centigrade for both country and Marmara region. Okay, I think this is the most important of the results of this study. Okay, this is maybe due to climate change or any other reason. Okay, this must be investigated in that very clearly. Result, okay, accurate determination of precipitation type in water-related studies is an important issue. Snow and rain directly affect the energy balance on all characteristics, evaporation and infiltration, loss and temperature distribution over the surface. Therefore, it's important to determine temperature at which snow and rain formation are equally likely. Accurate determination of critical temperatures clearly shows that it means not only surface variables, because we use only surface variables like temperature, weather, humidity, and so on. Okay, it means not only surface variables, but also weather condition beneath the cloud. Okay, the upper part or atmosphere over the surface. This is very important in determining critical temperature also. Okay, and this is the final result. Okay, increase in the critical, sorry. So increase in the critical temperature over time means that the snow will fall on a warmer surface. And therefore, it will melt before it has a chance to accumulate. This requires being prepared for serious water sort problems in the region where snow melt water is important in the water budget. Okay. Okay, here are some references used in the study. Okay, thank you. Şeyde kar ve yağmurun olasılığı %50 olan eğer artarsa bu nedenle daha yüksek sıcaklıkta da kar düşebilecek. Yani ama yüzey yapıldığı için yüzeyi ısıtan yeryüzü. Yani yeryüzü sıcaklığı. O zaman o kar sıcak ve yüzey üzerine düşecek. Yüzey üzerine düşen karın o da akımıyla yani toplaması, yağması ve erimesi. Bu özellikle su bütçesinin kara dayalı olduğu, Güneydoğu Anadolu, Doğu Anadolu bölgelerde çok sıkıntı olur. Sadece çalışmalarda ve başka çalışmalarımızda da aynı sonuç. Sıcak kapsamda buharlaşma artacak. Buharlaşmanın artması. Oluşumunu bu güçlendirecek. Bu da yağış. Bu da aslında başka bir konu. Bu çalışma sadece kar ve yağışın düşük sıcaklıkta olasılıkta düştüğü durum. Yani 5 derecede hem yağmur da yağar, kar da yağar. Daha yüksek sıcaklıkta da kar yağabilir. Karın değil de dikkatler öyle değil. Yağış esnasında yani hava bu esnada yağış devam ediyor. Bu yer klimatolojik çalışma bu. Yer klimatolojik ama bir de yağış bulutun altından yere gelene kadar o aradaki klimatolojik koşullar. Onu da düşündük ama onu yapacak kadar radyoda verisi lazım. Maalesef çok biliyorsunuz az sayıda Yes, please. Of course, yeah, right. The end of the study, find 0.5 something. Okay. Okay. And we also started the statistical test. This or the 0.5 is or not. In data, there's some problem. There's some data gap. And create this point attention. I mean, this result all the data considered together. Okay. Is Kamil Leziak now in the conference hall or not? No. Okay. So we must pass to the next presentation. The next presentation, okay, will be presented by Büşra Öztürk. Okay. The title of our presentation is Sea Surface Pressure Climatology of Cyclogenesis Patterns of the Black Sea. Okay, yes, Büşra Öztürk, okay, listen to you.
Master's degree student here in Istanbul Technical University, Atmospheric Sciences program. And I will present you my term project actually in Advanced Synaptic Meteorology class. And I have to tell that this is a preliminary work because I find new ways to enlarge this study. And it is about the Black Sea Law. The aim of this study is actually to investigate if there is a Black Sea low or not. And we know that semi-permanent low pressure centers are forming due to the topography and the atmospheric flows, larger flows. And their location and intensity is very important for the weather patterns for the vicinity. And similarly, the cyclogenesis over the Black Sea is impacting us in Turkey, and it is often mentioned as Black Sea low. And cyclone has to remain throughout the year to be named as semi-permanent pressure system, but previous studies in literature show that the Black Sea can have a high pressure area as well. And we need to confirm the presence of a Black Sea low and its seasonality and its frequency. When we look at the literature, we see that there are very limited research that studied on the Black Sea. One of them is made by Hussein and Muhammadi, and they stated that the high pressure area is dominating in the winter, but there is no direct research on the low pressure patterns. And other regions show that China, for example, the China Sea is more prone to cyclogenesis due to the coastal topography, and we can see the similar effect in Black Sea. I will show later in later slides. To form a cyclone in the east part of the sea. The data I used is AR5 reanalysis data with 0.25 degree resolution, and I obtained the hourly values and get the averages of the daily values. And temporal coverage is 1979 until the end of 2021. And you can see the domain here. And I used daily mean 2-meter temperature, different temperature, sea surface temperature, mean sea level pressure, mean wind speed, and daily total precipitation. And I analyzed the data with mainly Hohmiller diagrams. And when you get a data set, the first thing you do is generally to plot a time series. You can see on the left here. And these time series are annual average mean sea level pressure values. And you can see that there is no actually significant trend, but when you take a closer look, you can see that higher values were in very past and lower values are kind of occurring more for the recent year. And I obtained a monthly average mean sea level pressure value graph here in the right, and you can see that this is our clue that the Black Sea low could be seasonal, and it may be more common in the summer months. And when we look at the monthly average maps here, we can see that the legend is stable, like the same for every map, and January, February, March, April, and so on. And we can see that July is the lowest pressure values, as we saw in the previous graph. And we can see that the lighter colors indicate the lower pressure patterns, and it is mainly on the eastern and southeastern side of the Black Sea. And when we take the lowest pressure average for the graphs for the July, of course, we obtain this point, and we take both latitudinal and longitudinal Hohmiller diagrams here. The left one is this cross-section, and we can see that the mean sea level pressure for 43° north is showing us lowest pressure values in the summer, but it is mainly on the eastern part of the Black Sea, and we can see that the latitudinal change, and it is also lowest in summer months. And when we take only July months, and for the daily pressure values, daily average pressure values, and plot a Hohmüller diagram for that. We can see that the pinkish colors are more low pressure pattern, and we can see that the eastern part is more pinkish here, and it kind of confirms the location here. And low pressure patterns are more common in July between 2010 to 2015. You can see here more pinkish colors, and here. And Eastern Black Sea is experiencing more low pressure patterns for the last years, as I mentioned before. When we take a look at the sea surface temperature, you can see that the highest values, of course, in the August months, but higher in eastern part. You can see them here. This is due to the length. You can see here also. And southern Black Sea is warmer in terms of sea surface temperature. When we take a look at the different depression, which is temperature minus T point temperature, we can see that this is highest in the northern latitudes for the summer months and lowest in the spring months. And this is generally due to the topography. And I investigated the wind patterns by meridional and zonal because I thought that that could be something to show us the latitudinal or longitudinal change. And you can see the meridional ones in the right and left side for each one, and zonal winds here. And this is kind of, the winds are stronger in the summer months here. The colors are more significant, and zonal winds are stronger for the southern parts in summer. You can see here the summer months have brighter colors, and northerly winds are stronger in summer also. One of the significant results of the study is the total precipitation change by longitude and latitude. And we can definitely see that the highest precipitations are in the eastern parts and southern parts, and they are lowest. There are less precipitation in summer months. That is corresponding to this area, and we experience more precipitation in the eastern Black Sea region in Turkey. When we take a close look to the Pearson correlations between these variables, there is actually not a significant correlation between the parameters, but pressure and temperature are negatively correlated, you can see, and also dew point temperature. But there is maybe a clue about the moisture content of this study, that is mean sea level pressure is more significant rather than the temperature with the dew point temperature. But it is not a strong correlation, so we can just have a clue on that and investigate more. And stronger correlations are, of course, between the temperature and sea level surface temperature. To conclude, the results indicate a low pressure system in the eastern and southeastern Black Sea, and it is seasonal, of course, during the summer months. And we can see that the southeastern part of the Black Sea has sea surface temperatures higher, and zonal winds are stronger in that region. Pearson correlation did not gave us significant dependency on the evaluated parameters, but we can continue the research by categorizing the synoptic patterns of these cyclogenesis over the Black Sea. And one of the things that I'm excited about to perform as cyclone tracking and investigate the reasons why this low pressure pattern happens Is it by blocking, or is it persistent? Or maybe it could be a cutoff low. And the most popular topic is, some people call it hurricanes, but they are quasi-tropical cyclones, and their intensity could be increasing in the following years. And there are a lot of questions about this one, and I strongly encourage you to study these topics, because the literature is not enough, as I researched. Thank you for your attention.
Okay. Sorry. The next speaker is ATMOS'22. Can you hear us?
Hi. Hocam sesim geliyor mu?
Okay.
I'm starting. I cannot hear you, so I am starting. If something happened, you can interrupt me. Hello, my dear professors. I am Ecem Tuncer Uysal. I am research assistant and PhD student at Manisa Celal Bayar University. I am going to present you defining the meteorological drought trends at different time scales in the Aegean region that we studied with my thesis advisor, Assistant Professor Ahmet Ali Kumanlıoğlu. Defining and investigating the drought and tendencies of droughts in different timescales are significant for sustainable water resources management. Within the scope of the study, the standardized precipitation index method was used to define the droughts in different timescales. The intensity and duration of monthly, seasonal, and annual meteorological droughts that occurred in the provinces of İzmir, Manisa, Aydın, Muğla, Denizli, Uşak, Kütahya, and Afyon were investigated. In the study, wet and dry periods are determined by SPI method. The trends of droughts were determined by the linear regression method and Menkendal trend analysis method. Whether a change is expected in the drought trends in different time scales was investigated within the rescaled range analysis method. The Aegean region, located on the west coast of Turkey, covers 11% of Turkey with an area of over 90,000 kilometers square. The Aegean region, which includes the studied provinces, has a population of 11 million, means approximately 13% of Turkey's population. It covers the Gediz Basin, Küçük Menderes Basin, and Büyük Menderes Basin in the region. Trend analysis of meteorological droughts were performed using the monthly total precipitation observed between 1950 and 2017 at the meteorological gauge stations located in the centers of these cities. The geographical and basic statistical information of the stations used in the study are given in Table 1. The SPI method is an internationally accepted dimensionless indicator used to quantify meteorological drought, assuming that droughts are determined by precipitation variability, but other factors such as temperature remain constant and do not change over time. The SPI method, which needs at least 30 years of data, is calculated with a cumulative probability value with the help of a probability distribution to the observed precipitation values. The most frequently used distribution is the gamma distribution. Calculated cumulative probability values are converted into SPI index values with a mean of 0 and a standard deviation of 1 using equation 1 and equation 2. The drought classification of the SPI values calculated with the observed precipitation data is given in Table 2. Menkendal method, which is a non-parametric method, is frequently used in determining the trends of hydrometeorological series. Each ranked digit xi is used as a reference point and compared with the other ordered data, xj is using equation 3. Using the values calculated by equation 3, S is calculated by equation 4. The mean of the S-test statistics, which is normal distribution, is 0, and its variance is found by the help of equation 5. The term in equation 5 is used only when they are linked observations in the data. The standardized Menkendal statistic is observed by equation 6. In the study, the significance level was used at 95% confidence level. The cutoff value at the 5% significance level was taken as plus or minus 1.96. Rescaled range analysis, which is used in the determination of the variability of trends in hydrological time series, is also widely used to examine the variability in the drought trend. The variability, divergence, and trends in the drought series are explained by the first age coefficient calculated by RS analysis. The calculation steps are: drought index values are scaled, the data set Xi is subsequent. In the study, SPI time series were taken. Average is calculated for each subseries using equation 7. The additive deviation of each subset is calculated by equation 8. Interval sequences are calculated by subtracting the minimum values from maximum values of the cumulative deviation of the subsequence using equation 9. The standard deviation of each sequence is found by equation 10. The extended scales of each subsequence are calculated by dividing the values of R and S in equation 11. The regression equation between RS and H coefficient is given in equation 12. The coefficient H is calculated by converting equation 12 into linear logarithmic regression in equation 30. The slope of the linear logarithmic regression line gives the H coefficient. Variations in trends are interpreted depending on H coefficient. A coefficient of H is lower than 0.5 indicates the future trend will be the opposite of the past trend. The convergence of the H coefficient to 0 indicates that a future trend change will be highly probable. If H is equal to 0.5, is an indicator of randomness in the time series. If H is bigger than 0.5, the future trend series is similar to the past trend, and if the value converges to 1, it indicates that the trend in the time series is constant. In other words, if the trend in the transition is negative, it will turn positive in the future, or if it is positive, it will turn negative. According to table 4, MK is equal to and bigger than 1.96 means significant trend, and non-significant trend, which is MK is lower than 1.96, are determined with the MK analysis for all provinces. Here are the results. The linear trends of monthly, seasonal, and annual SPI values calculated from the precipitations observed between 1950 and 2017 in provinces which are given in Figure 2 and Figure 3. In the analysis of seasonal droughts, severe drought and extreme drought occurred in the seasons between 1973 and 1974 in Denizli, and from 1963 to 1974 in Afyon. When examining the changes, meteorological droughts in monthly periods, it is seen that all drought classes are occurred. Most of them monthly droughts were experienced in mild severe drought and mild severe wet classes in the region. Considering monthly, seasonally, and annual droughts, which are given in Figure 2 and Figure 3, dry periods are experienced from 1955 to 1958, from 1963 to 1964, from 1972 to 1973, from 1989 to 1993, and from 2006 to 2008 for all cities in common. In linear trend analysis, negative and positive coefficients show dry and wet periods respectively. According to MK analysis, there is a significant trend toward wet periods at the 5% significance level in the provinces of Muğla, Uşak, and Afyon in August, shown in red font color. Is analyzed that trend supports this opinion. However, randomness generally supports the non-significant degrees in the provinces for H is equal to 0.5 and shown in brown font color. H coefficient is calculated greater than 0.5 in all provinces in the examined region, means no change is expected in their monthly trends. In H coefficient is lower than 0.5, indicates the future trend will be the opposite of the past trends that are shown in blue font color. When the table 6 is examined, according to the results, statistically significant trends toward wet periods are seen in Izmir only for fall term, which is shown in red font color. On the other hand, table 6 shows that a change is expected in the drought trends of Denizli and Uşak provinces only for summer season, and a change is expected in the droughts of Muğla provinces on an annual scale, shown in blue font color. In the study, dry and wet periods of Aegean region provinces were defined by SPI method at different time scales. Then the drought trends of provinces were examined with the MK and LT analysis. The extent variability of drought dynamics was investigated by rescaled range analysis. As a result of the study, all classes of drought classifications were experienced in provinces of Aegean region. The drought tendencies of the region are towards the dry periods in January, February, March, and December monthly, winter seasonally, and general in relevant provinces annually. When MK, LT, and RS analyses are determined monthly, seasonally, and annually, results are obtained and shown in the table, which gives the results. All the analyses support each other. In conclusion, changes are expected in drought trends. Trends toward dry periods adversely affect water resources. For this reason, detection of drought probabilities and dynamics in advance is very important in terms of taking precautions for sustainable water resources management. And these are the references that we used in this study. And thank you for attention. If you have any question, don't hesitate to ask or connect with us. Professor, I cannot hear you. I cannot get your voice if you are saying something.
Hello, I think it is also important to calculate the standardized precipitation evapotranspiration index in order to see also the effect of changes in temperature, the warming trends for the droughts. Have you looked SPEI as well, or are you planning to look SPEI?
Actually, we use only precipitation values for this study, and the other parameters remain constant.
Okay.
Contribution. Okay. Ecem, can you hear me? No. Okay. Thank you, Ecem Tuncerüysel. Okay. Let's pass the last presentation of this session. Okay. The speaker is ready.
Yes, hocam, I am ready. May I share?
We are ready to listen to you. Okay. The title of this improvement of work model by utilizing artificial nerve. Okay.
So I'm starting now. Hello, today I'm going to present my study which covers implementation of artificial neural networks to work wind speed variable. Firstly, let me introduce myself. I am Mitap Kara and studying in Istanbul Technical University as a master's student. My speech will proceed in the order in which it appears on the screen: introduction, motivation, etc. With the OPEC oil crisis, it is understood that instead of oil and fossil-based fuels, other alternative energy sources should be found or supported. Also, Kyoto Protocol and Paris Agreement played an indirect role in climate change by supporting increased application of renewable energy systems. So total installed capacity has increased, as you can see, increased 8 megawatt to 650,758 megawatts in global. When we look at Turkey, where the wind power turbines started to be established in the 2000s, total installed power of wind plants in Turkey are increasing by years, as you can see in the figure. And the ministry aims for it to be 20,000 megawatts in 2023. In order to realize these potentials, consistent wind forecast should be made, but sometimes wind measurement may not be appropriate due to geographical and methodological obstacles. In that point, numerical weather prediction models comes to our aid. They can give us spatio-temporal information of desired variable. In literature, there are many studies. For example, Mater and Bovaran have investigated the performance of WRF model with ERA interim reanalysis data and in the Central Coast of Chile. In Turkey, Tan et al. Have investigated the performance of WRF on wind speed variable by running the model for the western regions of Turkey, Aegean region. And they used artificial neural network for the wind speed prediction and energy estimation. Let's continue with motivation. Wind speed is a difficult variable to predict and its forecast is very important since there is a non-linear relationship between the energy produced and the wind speed. The primary purpose of the study is to find out spatio-temporal performance of WRF model by model using GDAS data over Turkey. Second one is determine how much the artificial intelligence, how much the artificial neural network has improved the WRF model. Let's continue with methods. Also, I want to mention that the average altitude is about 1,141 meters in Turkey, and Turkey has different mountainous geographical features. We see that these features increase, we go east. Initial and boundary conditions are taken from the GDAS data, as you see in the picture. The wind speed data gathered from the Turkish Meteorological Service stations, which has which has a measurement at 10 meters. As you can see in the picture, some of these stations are located in the airport, some of them are in the rural areas. Here is our methodology, summary of methodology: collecting data, setting up model output statistics, applying artificial neural network, visualization and performance and comparison with work model, and result. Here is our configurations. Since the study area is across of the Turkey, the spatial resolution is chosen as 9 kilometer, and single domain have been used since we had a limited SPU power. Here is our VPS domain. Artificial neural network, which is a subset of machine learning, their name and structure are derived from the human brain, and they resemble the way real neurons communicate with one another. And the work procedure of neuron is easily understandable. The net input is calculated with the bias function by multiplying according to weights and summing of inputs which are gathered from the external environment. The environment can be methodological variables or music samples or video samples. The net output is calculated by passing the net input through the activation function. This operation gives the result of a cell. Activations function are indicators of a perceptron response. It specifies how the weighted summary or bias inputs convert to output. I personally, in that study, I choose ReLU function because in ReLU function, neurons are not active at the same time, and since it has not a asymptotic lower upper bound, so it doesn't trigger vanishing gradient problem, as you can see in the picture. The number of neurons, hidden layer and output neurons, and the choice of neural network configuration vary the problem of interest. As you can see, there are many heuristic methods for optimal network topology. I choose the radial basis function nets with Heck-Nielsen method in that study. Now we have a configuration of artificial neural network. We have warp pressure, warp wind speed, warp temperature, and observed wind speed, of course. Now the train and test data were randomly divided into as 70% and 30% respectively. Mean squared MSA loss function and Adam optimizer have been used. And in order to prevent the overfitting problem of the model, I put an early stopping algorithm in my Python code. Here are my results. When the overall average of Turkey is considered, measurements average is 1.77 meter per second. According to WRF, the average is found to be 3.5 meter per second, and ENR result was the same as observed, which is 1.77. As you can see, the model very overestimated the real results. At the first glance, it is seen that the output of the intelligence model, which is in input of the observed data, is similar to observation data, but the analysis with error indices and correlations, of course, will give more accurate results in the section. In general, WRF model Pearson correlation coefficient was found to be 0.5. In WRF plus ANM model was 0.56. So improvement rate was found to be 11%, as you can see in the figures. Also, WRF model, the absolute mean bias error was found to be 1.41. In WRF plus ANM model was 0.03. Improvement rate was found to be 97%. And we have a root mean square error was found to be 2.25. In WRF plus ANM model was 0.95. Improvement rate found to be 57%. And we have an index of agreement, which is the error matrix used in the literature. Is found to be 0.03. In War plus ANN model was 0.6. Here is the Taylor diagrams. In the following sections, the starting point of the red arrow shows the Wolf model, and end of the point is the artificial neural network. The success of the model is shown according to direction and status of the red arrow. As you can see there, we have a x and y axis. They show standard deviation, and we have an ellipsoidal structure that shows correlation. In Marmara region, correlation improved by 4% and the RMCA decreased 53%. In the Black Sea region, correlation improved by 17% and RMCA decreased 52%. In the Anatolian region, correlation improved 6% and RMCA decreased 48%. In Aegean region, we have a 11% improvement and RMCA decreased 66%. In the Mediterranean region, we have a 11% improvement and RMCA decreased 59%. In the Eastern Anatolian region, we have 26% improvement and RMCA decreased 50%. In the Southeastern Anatolian region, correlation improved by 25% and RMCA decreased 57%. To sum up, all in all, we have a WRF, ANN, and relative change columns. We can easily see that ANN improved wind speed by 11%, as you can see in the table. And here is the spatial distribution of improving rates by percent. It varies between 85% and 0.44%. Here are the suggestions. We see that using practical applications such as machine learning in improving model performance is very beneficial to use. Also, it is thought that such studies will contribute to natural emission targets of the goals of UN clean energy, which is the seventh one. First, it is thought that running the WRF model at a higher spatial resolution will increase the correlation between the model and the stations. Also, in order to find the maximum model performance improvements, WRF model with different physical schemes and their combinations must be run, and distinct topologies having different activation functions must be tried. Then examining the difference between these combinations on a spatial temporal basis will enrich the study. In addition, it is thought that a dropout layer can be added while training model into the Python code rather than just using a patience in order to avoid overfit problem. Also, I want to mention there are some pitfalls in there. We also checked the locations of several stations having very low correlation value for expanding our perspective, and we found that the reason for the errors may not only be due to the model or measurement, because as we can see here in Adıyaman Turkish Meteorological Station, located at the very distinct place that there are tall buildings in the surroundings. They cut off the wind. And in other example, the station is located at the terrain that shows a valley structure. Considering that the mountains change and direction of the strength of the incoming wind, low R value may be result from the topography in the model. As you can see here, we have a different mountain ranges in around the Tunceli station. Thanks for your patience. Thank you. Here are my references also. Hocam sizi duyamıyorum.
Okay, again, thank you for your participation and the contribution to this session. And I think there's a COVID break. The following session will begin at 11:30. Thank you. Güzel teşekkür ediyoruz katılımınız için. Sağ olun.
Anlamıyorum hocam, yani görüyorsunuz bir saat önce konuşuyordunuz, gidiyordu ses.
Ya bunlar olur. Bunlar yapacak bir şey yok.
Yani tam çıldırmalık.
Önemli olan sonra
Anlamadım ki. Geliyor mu sesim? Bir tak bakalım. Ses 1, 2, 3 ses. Evet, biliyorum. Ses 1, 2, 3 ses deneme. Sesimiz az geliyor değil mi? Mikrofonun bu tarafı, bu tarafı, bu tarafı. Ses 1, 2, 3 deneme. Geliyor mu? Ses, ses, ses. Ses, ses, ses. Deneme, ses, deneme. Ses, ses. Ses, ses, ses. Ha, evet, evet, evet. Oturdu. Ses. Geliyor mu ses? Arttır bence biraz daha. Ses 1, 2, 3. Ses. Otomatiğe alsak. Aa bak şu an az önce sanki bayağı bir yükseldi sesim de. Ses, ses, ses, ses. Ses, ses, ses. Ses, ses, ses, ses. Ses. Ses. Geliyor mu? Nasıl oldu? Şu an bayağı yükseldi sanki ama geliyor mu ses? Bak oradan görüyordum yükselmişti. Bak şu an arada sırada yükseliyor. Ses. Ses 1, 2, 3. Ses, ses, ses, ses. Evet hocam o bozuk. 1, 2, 3. Bir ara yükseldi yine. Ses, ses. Ses, ses, ses. Ses, ses. Ses, ses. Ses, ses. Ses, ses. Ses, ses, ses, ses, ses. Ses, ses, ses, ses. Ses. Geliyor mu şu an? Yakada tutunca yok ses. Bak şöyle konuşursa falan bile kafasını kaldırıp hiç. Böyle aşağı doğru tutarsa geliyor. Mecbur elde tutacağız bunu. Bunu kendi Windows ayarlarından aktaramaz mıyız sesi? Problem ne ki o zaman?
Şu an kamera da bakıyor. Nasıl? Çok kötü. Bayağı kötü. Evet. Ses bilgi şu bu anlaşılıyor.
Mikrofonu aldım.
Şu an
Buradan.
daha iyi.
Bu daha iyi.
Ama bu nereden peki? İç mikrofon dedi.
Bilgisayar. Bilgisayarın
Bence o
sesi.
buradan iyi gibi. İç mikrofon mu yapsak onu da? Yani konuşmacıya vereceğimiz
Şu an bu
zaman
iyi gidiyor mesela. Şu anki hali bile iyi gidiyor. Bundan daha iyi.
değil mi? Peki onu iç mikrofon yapsak oradan oraya sesi gider mi? Sonuçta
Şunu mu? Onu mu kullanalım?
hayır şimdi bak iç mikrofonda kalsın ben orayı açayım.
Şey dış
Hoparlörden
hoparlör
ses oraya
anlat.
geliyor.
Ben de onu diyecektim tam. Konuş bakalım orada.
Ses. 1, 2, ses, ses. Geliyor mu?
Geliyor.
Nasıl? İyi mi peki?
İyi geliyor.
Bence o zaman iç mikrofonda kalsın. Bunu yaka
Tamam, bir de
mikrofonda
şuradan konuş.
ses.
Tamam. Öyle daha iyi. Abi
Bence
yakın
de-
mikrofonu falan uğraşmayalım.
Bence de iptal et. O zaman sök istiyorsan hatta diye. Böyle kısık sesle falan konuştuğunda da geliyor mu?
Geliyor.
Hani böyle sessiz
Evet,
konuşuyor.
bu daha iyi.
Tamam o zaman iç mikrofonda kalalım. Şimdi sen şeyi
paper of determination of microplastic in the range. Açsın yalan. Arzu Meral olabilir mi? Hani Türkiye bileşeni var galiba sunumun, çalışmanın da. Batuhan Kibar, Arzu Meral. Gülen Gül, evet. Bu sunulmayacak mı acaba? Burada. Peki. Let's begin, okay? We're waiting for the information. Let's begin. Welcome to the second session of today's. The topic of this session is atmospheric environment. And I am Mr. Katırcıoğlu from Metallurgical Engineering Department. We have 6 speakers today in this session. And each speaker will have 15 minutes. 10 minutes will be enough, I guess, will be enough for the presentation, and we can use last 5 minutes for your questions and answer. So let's start with the first speaker, Mr. Dimitrios. I'm sorry, I forgot my eyeglasses. Melas. His presentation is estimating the cooling degree days evaluation under climate change. So, right now.
Okay, thank you. I'm really happy to be here in Istanbul to join the conference. I would like to thank the organizers for this opportunity. I'm Dimitris Melas from the Aristotle University of Thessaloniki, and my presentation today will focus on the urban heat island. Actually, this is a study focuses on the urban heat island. However, we are going to also see some results about the present and future climate in Thessaloniki and Rome, and try to show some results for the cooling degree days under climate change. Starting with the methodology, we use the UF model as a climate, regional climate model. The input data come from CIMIC 5 under the scenario RCP 8.5. The resolution of the input data is 1 degree. However, we also use a very high resolution dataset for land use. We have used this data to downscale our results down to 250 meters. So, although the native resolution of the model in the urban areas was 2 kilometers, we have downscaled down to 250 meters. The simulation periods were covered 3 time slices, 2006 to 2010 for the present climate, 2046 and to 2050 for the middle of the century, and 2096 to 2100 for at the end of the century. As I told you before, the finest resolution was 2 kilometers. That was the resolution over the 2 cities, the urban areas of Thessaloniki and Rome. However, we used the nested domain covering the areas that are shown on the map. the definition of cooling degree days. You can see to the right the equation we used for calculating them. The input parameters we use towards the average temperature, the maximum temperature, and the minimum temperature of the day, with a base temperature of 22 degrees. Before showing the results, I will show you the results of the evaluation of the model we have done. This shows the comparison of model results with 1 year observational data. You can see to the left the results for Thessaloniki, and this is for Rome. Overall, we are very satisfied by the agreement. You can see that we have used 5 stations in the urban area of Thessaloniki. The mean bias was, say, almost below 1 degree Celsius for every station. So the average is 0.61 degrees Celsius. The index of agreement was very good. Actually, it was 0.96. Things were even better for all. You can see that the model slightly underestimates temperatures in Rome. However, the overall bias was only 0.36 degrees, and the index of agreement was even higher than Thessaloniki, 0.98. These are the maps for the average summer temperature for the present climate and the climate by the end of the century. The municipalities, actually, not the urban areas, are denoted by a white line. And you can see that there is a clear footprint of the urban area. Here you can see Rome, and here you can see Thessaloniki, exhibiting temperatures that are higher than the surrounding rural areas. The same applies to the end of the century. Of course, here temperatures are quite higher. However, you can still see the urban island effect over these areas. Just to have an indication of temperature change, it's plus 3.5 degrees Celsius in Rome and plus 4 degrees Celsius in Thessaloniki for the end of the century. Here we have some results concerning the urban heat island intensity. The intensity is actually defined as the difference between temperature in the city and the temperature in the surrounding rural areas. The results are for intersections that are shown here. This is for Thessaloniki. You can see results across this intersection, and this is for Rome.
Geldi mi link? Atayım mı?
Solid lines show the mean temperature, dotted lines show the maximum temperature, and different colors show different time slices. First of all, it's obvious that future climate, which is the uppermost curve, exhibits the warming trend. That's for sure. But we have already explained this. What is more interesting to see is that when comparing the differences between the urban center and the surrounding rural areas, differences for the minimum temperature and the maximum temperature, we can see that the minimum temperature certainly exhibits higher values in the city center. The city is located here, while the maximum temperature is not affected. The minimum temperature in the urban areas is about 2 to 3 degrees higher in the city center than in the surrounding areas, while for the results for Tmax are those. You can even see slight cooling inside the city center. This is attributed, of course, to the fact that heat is stored in the buildings, resulting in slightly lower temperatures in the city center early afternoon hours. For future climate, what is interesting and positive, I would say, that the weak intensity remains remains constant, meaning that the difference between the city center and the rural areas in the future climate is approximately the same as it is in the present climate. However, this occurs, of course, in a new temperature range. You can see here in the present climate, for Thessaloniki, temperature range is 25 to 31 degrees, while at the end of the century it goes up to 29 to 35 degrees Celsius, and the same in Rome, slightly lower, but still exhibiting the same increasing trend. These are the results for the CDD, the cooling degree days. It's a bit complicated. I'll try to explain this. You can see results for the different months. Here, of course, to the left, you see Rome. To the right, you see Thessaloniki. The three curves are for the three time periods, time slices. And this is for different parameters. This is the mean daily CDD, and this is the monthly accumulated CDD. Actually, they show quite similar results, so I will not comment both of them. What you can see is that the difference between the present climate and the climate at the middle of the century are small. We see an increase, a slight increase of about 1 degree daily, which is a small value. However, this increases considerably if we move to the end of the century, where this difference is 3 to 4 degree days. There is also a slight change in the overall pattern, not so much in Rome, but in Thessaloniki. Please observe that in the present climate, the month with the highest needs is July. This is the highest value for the present climate shown by the green line. And August is the lower. If we move to the end of the century, this is the reverse. July is slightly lower than August. This is the percentage difference in the accumulated number. Again, this is Rome and this is Thessaloniki. The orange denotes the middle of the century. The red color denotes the end of the century. And you can see rather, unexpected value, paradox, that May, by the middle of the century, in both cities, exhibits a decrease, a percentage decrease in the occurrence of CDD. However, all other months show a positive trend below 50%, but this is only one extreme value. In general, below 40% for both cities. This is for the middle of the century. Results for the end of the century are always positive. If they exhibit much higher value, you can see we can reach almost 125% increase compared to the present climate. This is the distribution of the days with the distribution of CDD days. And these are for the present climate. Rome, Thessaloniki again, the different colors show different months of the year, always focusing on the warm part of the year, not summer only. We have extended, including also May and September in this period, not only the summer months. So in the present climate, Rome, most of the values in Rome are between 0 and 6 degree days. There are a few in 6 to 9 during July and August, but most of them are here. In Thessaloniki, we have a shift towards higher values. Most of the values here are from 0 to 9, and there are also a few days for 9 to 12. There is an increasing trend during for the middle of the century. Actually, we moved 1 pin to the higher values from 0 to 6 before. Now we have 0 to 9 and a few values, 9 to 12 for Rome. Sorry. This is wrong. This is Rome and this is Thessaloniki. Sorry, I apologize. And the same applies for Thessaloniki. No, so I will correct again. Okay, so this is Thessaloniki actually, and this is Rome. For some reason, I have put the reverse order. Yes, sorry, absolutely. This is Thessaloniki actually. So now we have the appearance of this sector, 9 to 12, which was not present significantly before. And the same applies for Rome, where we have values in 6 to 9 also. And of course, the highest values are found at the end of the century, 0 to 12 for Rome, and a few cases higher than 12 actually, and 0 to 15 for Thessaloniki, and a few cases 5 to higher than 15. What is interesting is that the temperature climate in Rome by the end of the century shows a similar behavior than the present in Thessaloniki. Rome is situated higher latitude than Thessaloniki, generally has lower temperature. So by the end of the century, the distribution in Rome will resemble the one in Thessaloniki for present climate. So I see that I have already used my time, so I will not present again the conclusions as I already explained them. If there are any questions, please.
Yes, we have a question. You.
Congratulations for the presentation. I have one question. In one of the slides that you mentioned that the urban heat island intensity remains constant, but I wonder if you have you ever considered that the urban structure is also going to change in the future, and have you ever make any possible simulations that including heat changing structure?
This is a very good question, actually, because in most of these studies, we assume that certain parameters remain constant. And this is not the case. However, with the present knowledge, it's not possible to imagine or to calculate, estimate how the urban structure will change in the next 80 years. Sorry, so your question is exactly to the point. I fully agree with you, but we don't have the tools today to estimate, well. Okay, so take this as the climate perspective, not including the other parameters.
Question? Thank you very much.
Thank you very much.
Okay, the next speaker is, I think, Yes, and the title of presentation is a case study variation of volatile organic compounds levels during the lockdown period of COVID-19 pandemics in Turkey.
Hello everybody, my name is Bana and this study was conducted with my master's student Nige, and she will also have a presentation after me. And I will start with the background of our study. So this study is about air pollution, and as you know, air pollution has a very concern worldwide, and it is one of the important causative agents to cause human adverse health effect, and that's why we care about the air pollution. And last World Health Organization report says that air pollution, both indoor and outdoor air pollution, cause cancer, and we have some carcinogenic compounds that we know to human beings, such as benzene. And we have so many pollutants, and we have to decide which one should be measured, which one should be monitored for a long term. And in this study, our target compound group was volatile organic compounds. Those are very popular for the last 2 decades. And they are emitted mostly from anthropogenic sources, and they have a very important effect on atmospheric chemistry as well. Okay. I don't know what's going on. Okay, no. Oh. I'm just trying to move on, but then.
Bakıyoruz hocam bir şey.
Let's try again. Yeah. I'm sorry.
Yeah, it's okay.
21, I guess. That's working now. Uh-oh. Oh.
Is this next section?
Yeah, we can move on with this one. So we have the classification system of volatile organic compounds depending on the boiling points. And we have very volatile ones. Their boiling points are up to 100 degrees Celsius, and we have the moderate range between like 50 to like naphthalene to 140 degrees Celsius. And also we have semi-volatile organic compounds that can be in also particle phase. They have higher boiling points, that's why they are heavier than the regular VOCs. And also we have particulate organic materials. They are adsorbed on solid surface, and they are the heaviest ones. And you can also give apparent concentration about the volatile organic compounds, because in this group we have so many compounds. They can be in alcohols, they can be in aliphatic groups or aromatic groups, but to make the calculations easier and to make a clear perspective about the composition of the air in terms of volatile organic compounds, we have a term called total volatile organic compounds. Mostly it refers to compounds between n-hexane to n-hexadecane, so it's the sum of VOCs in this range. And VOCs cover a large group, so mostly we observe aromatic hydrocarbons, paraffins and olefins in the air. And the type of VOCs and its level are dependent on the characteristics of the source. If you are close to traffic, then maybe you have like benzene, toluene, benzene more. If you are close to a factory, depending on the solvent used, you can have different compounds. And studies show that VOCs can also exhibit a seasonal distribution. If you are using solid fuel for domestic heating, mostly in the winter time, you have higher VOC concentrations than summer. And why we care about VOCs? Because there are so many potential sources that emit VOCs. Almost everything that you can see has a potential to emit VOCs. And they are important in terms of reactions, atmospheric chemistry. They can be reactive. Some, especially we have some groups, they are much more reactive and they pose an important role for photochemical smoke. And they can also trigger chain reactions because it's not like the reactions occur in the water. In the atmosphere, we have mostly chain reactions and it can trigger or they can be intermediate compound within the chain reactions. And most importantly, some of them are already classified as carcinogenic compound like benzene, and some studies are ongoing and there are some clues that some VOC types can also be carcinogenic, but maybe 10 years later we will have another list to show the carcinogenic VOC list. And what is the motivation of this study? As you know, during COVID-19 national lockdown period, and we had a lockdown period in Turkey, which was also covering the religious fast. And between April 30 to May 17, we had a curfew, and we had to stay indoors constantly because it wasn't allowed to go outside if you don't have an emergency work or if you don't have permission. And that's why the hypothesis was people had prolonged indoor air pollution exposure during the curfew. It was the hypothesis, and we in the study we covered VOCs both indoors and outdoors. So we had simultaneous measurements during this curfew, and we tried to take sample every day. And of course, I use my home because during the curfew it's not possible to go another people's home and take the sample. So it was my living room. And I took indoor sample from my living room, and also I used my balcony for outdoor sampling. And the problem is curfew is announced 1 day before it starts. So 29 April was the announcement date for the curfew, and curfew started right away. And during the curfew, we had religious fast between 13 and 15 May, and the curfew finished 17 May. Yes, this covers only the curfew period, but if you want to compare or if you want to show the effect of something, then you have to compare it with something like reference condition or post condition. That's why we extended the study 1 month more after the curfew ends. Therefore, we had a chance to compare the effect of curfew and after the curfew. So that's why the sampling period covers starting with the curfew and ends like 17 June. So this is the study site. This is let me try. Yes. This is Çanakkale. It's the very western part, located very western part of Turkey. And you can see the location of Çanakkale closely. And this was the starting point, my house. So, and you have more information about the location here. And since the curfew started at 7 p.m. on April 30 and ended up at 5 p.m. on May 17, during the curfew, maybe different countries apply different restrictions for the curfew periods, but in our national one, It was called full lockdown policy, and education and works were suspended at all levels, and exams were postponed. Traveling with the city and or with out of the city, as well as driving a personal vehicle was banned. Merely people who work for emergency tasks were allowed to be outside the home with a special permission. Yes, we had a chance to go to the lab because we had an ongoing study, so we took the permission for just a couple of hours during this curfew, but the rest of the population had to stay at home. This is the picture from my balcony. Yeah, this is actually Gardenal Street. And there is a traffic junction here, and there is a traffic light on this junction. And the characteristics of the study site in the environment, we had on average 2 to 3 people in the sample room during the sampling, and windows and doors were kept closed during the sampling. No one was smoking at home. No wet cleaning with the household agent was done prior to sampling. Sampled room had surface area of 30 square meter and equipped with 4 couches, a dining table, and a TV covered with wooden floor covering. And renovation date for the building and the house was over 5 years, and it was laid on the 5th floor. And we had facade to direction of a paved road, and here, this is the paved road, so the building is here. And okay, so I will try to be, okay. So, and let's go on with static analysis method. Daily VOC samples were collected at 4 p.m. By low flow air sampling pump according to active sampling principle. We had dual sorbent tubes, and we collected VOC samples into sorbent tubes, and then we quantified and qualified the VOCs by using thermal desorption and gas chromatography device, and then we according to the calibration result and also indoor-outdoor temperature, relative humidity were recorded during this sampling. Let's look at the results. Total VOC concentration during the curfew lockdown period for indoor and outdoor environment, as you can see, VOC levels were higher inside the room than outside the apartment. And this difference is statistically significant. And also we have this similar picture for the most important VOC compounds called benzene, toluene, ethylbenzene, and styrene. As you can see, in any case, indoor levels are higher than the outdoor levels, and this difference is significant for benzene, toluene, ethylbenzene, and styrene. And we also calculated indoor to outdoor ratio. What is indoor to outdoor ratio? If you are making this simultaneous measurement for both indoor and outdoor, you have to calculate this to find the potential source contributors. And if this ratio is higher than 1, potentially you have additional sources inside your indoor environment in addition to outdoor sources. And here, indoor to outdoor ratios were compared during the lockdown and after the lockdown period. The yellow one shows the during the lockdown cases, and mostly indoor to outdoor ratio is higher than 1 as average or median value. So this means we had more sources inside the home than outside the home. But then for post cases, for some compounds, we have almost similar indoor to outdoor ratios, even the range is not that wide. And also we compared the concentrations of VOCs during the lockdown and after the lockdown. Only those 3 cases were statistically significant. That's why I will show them. As you can see, it is a bit interesting because during the lockdown, benzene, indoor benzene, outdoor benzene, and indoor TVOC levels are lower than after the lockdown case. So this is interesting, but I was expecting this. You can say that maybe it should be lower because people had a chance to go out while we had more indoor benzene level or indoor TVOC level after the lockdown. Because the time period was like spring or almost summertime, so we have the Mediterranean climate region, so this means we are ventilating our homes by opening the windows. This means if you have a higher outdoor concentration in terms of VOCs, outdoor VOCs contribute to your indoor VOCs by ventilation. And we have the correlations between indoor VOCs, outdoor and outdoor, and indoor to outdoor concentrations. We had this for during and after the lockdown periods separately. As you can see, indoor, there are correlations between the compounds measured indoors for during the lockdown, and we have correlations between outdoor to outdoor VOCs, but we don't have any correlation between indoor to outdoor counterparts. So this means actually, potentially their source contributors are not the same. As a conclusion, in this study, we determined the COVID-19 pandemics and it has a contribution on VOC levels, especially in the indoor environments. And during the lockdown, people had to stay indoors constantly and with that prolonged exposure to many indoor air pollutants like VOCs. And VOCs were higher indoors than outdoors. Indoor to outdoor ratios for those VOCs were greater than 1. We can skip this one. Since there was no statistically significant relationship between levels of VOCs occurs indoors and outdoors counterparts, the main sources of VOCs were not common for both environments. Potential sources of indoor VOCs might be due to human activities and occupancy, while outdoor VOCs might have originated from traffic sources with low density, as domestic heating couldn't be a source in the warm season. After the lockdown, particularly outdoor VOCs levels increased probably due to the contribution of traffic sources and related human activities. And this is maybe the only study conducted around our region. Thank you very much.
Do we have any question? So much.
Yes, a question.
Nice presentation of experiment.
Thank you very much.
You showed that the outdoor VOCs have been increasing in the post-lockdown
yes,
period.
Mm-hmm.
But I was thinking that maybe this difference is even higher because we have the seasonality. So because during we have the seasonality with higher concentrations of VOCs during the winter time or because of less reactivity.
Yes, but it wasn't like July or August, which catalyzes photochemical reactions. So the months and the temperature trends are almost similar. I think traffic is the main source because I couldn't mention because of the time limitation, but I also counted the cars passing on this traffic junction. And the number of cars passing during the lockdown and after the lockdown are completely different. And yes, and so since we were at home, we had limited activities outdoors during the lockdown, but when people had a chance to go out, of course, activities related to human are increasing. Thank you.
Thank you. Any question? Okay. Thank you very much. Next one, okay. The next speaker is Müge Aydın. The title is Air Quality of Gallipoli, Turkey Aftermath of COVID-19 National Restrictions.
First of all, hello everyone. I am an environmental engineer. I am here to tell you about our work titled Air Quality of Gelibolu Aftermath of COVID-19 National Restriction, which you can see in the picture today. I hope it will be a good presentation for everyone, especially for me. Before I start the presentation, I would like to talk about a presentation flow. I will explain the basic concept and goal, and then I will explain the applied material and method, and then I will explain the result and completed presentation.
Zoom'da ilerliyor mu? Zoom'da ilerliyor mu? İlerliyor. Buraya gelmiyor. Tam ekran yapmanın da bu şekilde.
Yes, we are having a problem with projection.
Oradan ileri. Baştan ileri.
Ben mi ilerliyorum?
Şimdi de Zoom'da değil ama.
Zoom paylaşım.
Zoom paylaşmıyor. Zoom'a geldi.
Okay. I will move on.
What are the factors that affect air pollution? We can broadly divide it into four groups: constant, moving, point, is area, and natural research. The constant of our work are moving research, for example, automobile, aircraft, train, and ship. And in this respect, there are factors and sources, for example, geographical condition and meteorological condition. Okay. Urbanization, transportation, and industrialization are most important why air pollution has become widespread on health problem, public health problem. These three sources influence each other in vicious circle. In addition to air pollution from fixed emission sources such as industrial, exhaust pollution from motor vehicle in important problem. Currently, the number of motor vehicles in Turkey is about 25.5 million. Yes. Although air pollution level are regularly monitoring and compliant, they are still above accepted limit all over the world, especially in metropolitan area. In Turkey, there are air quality monitoring stations run by the ministry, all the provisions, while there are pollutant groups such as particulate matter, sulfur dioxide, carbon monoxide, nitrogen oxide, and ozone emission risk criteria. These stations, there are pollutant groups, not criteria. There are pollutant groups you see, bioaerosol, black carbons. Yes, so why is air pollution important? I have talked a little bit about its environmental effect, but it also has great effect human health. Air pollution is an important risk factor for health in our country and all over the world. Air pollution causes deterioration, especially in respiratory function. In general, we can say that there are acute and chronic effects. So far, I have given general information about air pollution and important parts. Now we will go into more detail by station. The aim of this study is to determine the relationship between the traffic, which is the main sources of VOC, and the examine types and levels at different sampling points in the area. As you can see, the pollutants are volatile organic compounds. There are many compounds that fall into the volatile organic compounds class, and some of them are toxic and cancerogenic, for example, benzene. They are play the information of concomitant smoke. We move on the most beautiful and exciting presentation for me. The region work is Gelibolu, and its population is about 44,000 people. And since the town of Gelibolu is on the shores of Dardanelles and in the weather of the year, yes, it has been determined that number of fuel tonnage, pickup and trucks, and transported throughout Gelibolu and Lapseki line is more than 3 times, and the number of trucks transport is about 13 times, 35 times higher of the Çanakkale Dardanelles stated harbor line. Yes. We study was carried out 12 passive sampling total points. These points have been preferred because they are a location where there are both vehicle and motion and main parked vehicle. Within this scope, 9 and 12 passive sampling point location in the Iran's Gelibolu ferry line. And two outside tools in this G10 and G11 and one point background. Yes. What is the method we used in this study? We will talk about it. These samples were collected by passive sampling method from outdoor air into 10 STI carbograph thermal dissolving tubes, and the tubes were changed and invented 50 and 20 days only. Yes. In this line is the result of a study. I will describe a general result firstly. What you see on the table is actually the mean values taken from the Lapseki and Çanakkale air quality station data, and temperature and wind direction are given. So our study look points between 22 June and 3 November. So as you can see, TVOC and particle matter and ozone increase levels after 12 July and 4 August. Yes. Yes. In general, VOC levels increase by degrees of the study period. For example, TVOC in level was observed by a hike in G9, and benzene level was observed by G8, and toluene G6 between 22 June and 30 July, and the high xylene levels observed by hikes at G8 between. Yes. Evet. Sabah da böyle mi? Burada mı yaşıyor?
Zoom'u ver o zaman. Bunu ver.
Ne vermemiş? Ne gitti ama? Gidip gidiyor.
Okay, in the first figure, the overall rate, the mean of the BTX group over the period of about 6 months, benzene, toluene, and xylen were measured hikes at G5 and G8, and in TVOC hikes dissipation at G10 and G11, and then G3 and G9. Yes. When we look at the change on the basic pollutants throughout the whole study, actually for the first time after 12 July and 4 August, serious increase VOC levels. Yes. Figure 6, seasonal variation of BTX compounds concentration in yellow blue. Normally, more intense traffic is observed in summer. The reason for the effect of COVID-19. The period when we started working was period when the bonds were lifted. There was an increase in traffic, evident from the results. Yes. Table 1 shows the relationship between levels, VOC levels, and other air pollutants, Çanakkale Air Quality Monitoring Station data. Positive correlation were found between benzene and toluene, and xylen. Cross correlation were also found between VOC levels, sulfur dioxide, and benzene. Yes. Table 2, correlation was made according to values in last year. Positive correlation were found between benzene and toluene, and benzene and xylen, and benzene and nitrogen oxide. Yes. In this study, the temporal and spatial variation of VOC were investigated in 12 different sampling points in yellow. The same increased trend was observed for benzene, toluene, and xylen as well. And also VOC levels showed a negative correlation between ozone levels over study period. Since this study has been the first study conducted in Gable until now, it is thought that the result will contribute to real traffic-based air quality in the region. Yes. Thank you so much.
Thank you. Any question? Thank you very much. So, is the next speaker here Afsun Karan or Parisa Babay or Arzu Meral or Batuhan Kipar veya or no? It's not going to present. Let's move with the next one. The next speaker will present online. Mansur Ahmet Bat. And the title is Characterization of Indoor Airborne Microplastics in a University Campus. No, I'm sorry. Yes?
Yeah.
Yes, yes, okay.
Yeah.
Bir tane kaldı artık. Okuyamıyorum ki.
Should I share the screen?
Okay, Mr. Bat,
Uh,
you can start.
can you see my screen?
Not on the...
Can you see my screen?
Yes, we see, man.
Okay, okay. So it looks like I'm audible now. Okay. Characterization of indoor airborne microplastics in a university campus. Before going to the main topic, what we did and what was our aim and goal, I want to give a small introduction about the microplastics. As we all know that microplastic is a new global virgin pollutant, and its definition has been given within the size range of 5 millimeter to 1 micrometer. And there can be generally two types of microplastics. It can be primary or as a secondary. While as the common microplastics that has been found in the environment are polystyrene, polyvinyl chloride, polyethylene, etc. Now directly going to the objectives or the aims of the studies was to find out the presence of microplastics in different indoor environments, especially in the air in the university campus, and what was their shape, color, or the chemical characterization, and to find out their exact sources if possible. Now coming to the materials and methods, what we use the active sampling to collect the air from the different indoor environments like laboratory, corridor, and the office during the COVID time 2021. Active sampling was using with the usage of filters, Teflon filters, and the flow rate for the sampling pump was 9 liters per minute, and sampling was done for the 8 hours. Accordingly, questionnaire was filled by the occupants from these laboratories, corridors, or the offices. Now coming to the morphological characterization, I can say that during the materials and methods, what we did, firstly, we did the morphological characterization. For that, optical microscope was used. Later on, we used micro Raman for the quantification of the polymers, and finally, the analysis of structure elements or the additives if present or the contaminants that are absorbed by these microplastics was done by SEM-EDX analysis. Now coming to the results and discussion of the optical microscope analysis. And the morphology of these microplastics was done by the optical microscope. It shows us the presence of different fibers, fragments, pellets, etc. In the right side, if you see the figure, this is a general typical representation of the different microplastics under the optical microscope. These microplastics were seen in different indoor environments. The size of these microplastics was greater than 2.5 up to the 551 micrometer. These microplastics were having the different colors from brown, green to yellow, white, and etc. A considerable variation in size, shape, and color of the microplastics were seen. This can be probably due to the different sources of these microplastics in indoor environments. Counting of microplastics was not possible. The reason was that due to the smaller size, if we would have tried to count these microplastics, this would have definitely affected the count size due to the smaller size, and this might be the more difficult for the smaller size of microplastic, like if we'll talk about the nano size microplastics. In order to overcome this issue, we try to read just to the small portion of the filter, that was 25 to the 30% of the filters. I cannot go to the other slide. So under the micro Raman, we saw the 20 different types of microplastics in the different indoor environments of the university campus. These microplastics were like the Teflon, high density polyethylene, polyvinyl chloride, or the polypropylene, etc. The concentration of these indoor microplastics was almost between 12 and the 18. However, the laboratory was having the highest concentration, whereas the office was having the medium, and accordingly corridor was having the lowest concentration. The variations among these microplastics were seen in these indoor environments, like the laboratory were having the 20 different types of microplastics were seen, while in corridor 13, however in office 18 different microplastics were seen. We can say that the different sources in these indoor environments might be the textiles, printers, or the plastic packagings, etc. However, the ventilation can also affect the microplastic movement from outdoors to the indoors, or the clothes which are worn by the teaching staffs or the students or other non-teaching staffs can also be the source of these microplastics, especially the fibers. These are the typical representation of our microplastics, the micro Raman spectrums. In total, 25 different types of microplastics were seen. In left side of the figure, you can see 13 different microplastics, while in the right, 12 different microplastics were seen. Now coming to the other analysis, in order to find out the structural composition of these microplastics, or if the contaminants or the additives were absorbed by these, so we did the SAM-EDX analysis. The spectrum shows the general typical structure of the SAM analysis, while in the right side it shows the EDX analysis. The common structure elements were carbon, oxygen, gold, sodium, and etc. In general, the variations were seen among these elemental analysis in the microplastics. This can be due to the different types of the microplastics that were seen. This table shows us the different types of sample locations. In right, if we will see the laboratory, corridor, and the office. In the left side, in one column, it shows us the 3 different types of the microplastic samples were seen, microplastic 1, 2, and 3, and accordingly shows the weightage of each and every element. Although there were the common elements found, but still the differences where that might be due to the different types of the microplastics which we have seen, as I already told this. Now, in conclusion, what we can say, the microplastics were seen obviously in all the indoor environments. Their size was greater than 2.5 to 551. And the common microplastics that we see were the fibers, fragments, films, and etc. They were having the different colors. The common colors were black, gray, brown, green, and etc. A considerable variation was seen in shape, color, and in their polymeric composition. The concentration of indoor microplastics in the corridor, laboratory, or lab was almost between 12 to the 18, whereas the common structural elements were like carbon, oxygen, fluorine, and etc. And finally, I would like to thank the Eskişehir Technical University who provided the support for this project, and especially I would like to thank the Presidency for Turks who provided my PhD grant. And we would also like to thank the Dr. Gülipek, Dr. Ferdin, Dr. Nihan Kosu, and Dr. Sarvet Tonan for giving us access to use the optical microscope, micro Raman, and the SAM-EDX microscope. Thanks for listening. I'll be happy to get the questions from you.
Thank you. Do we have any question? No? Thank you very much, Mr.
So the Life Index project developed this online tool, this web page. In the tool, the user can see air quality, so results, concentrations, exposure, dose, and viral disease. We have 5 case studies, 2 in Portugal, Lisbon and Porto, 1 in Athens, Treviso in Italy, and Quavio in Finland. So the tool has 2 main modes. So the first one is the scenario mode. So the user can see emission maps, concentration maps, population, exposure, dose, and viral disease parameters. And there is a second mode. In this mode, the user can test different mitigation measures, for instance, traffic measures or residential conduct measures. And inside the tool, the emissions will be recalculated, and then new emission maps will appear, new concentration maps, new population exposure, new dose, and new viral disease parameters. And of course, the time activity partner can be also changed. Here is the layout of the tool. So there is different menus. Here you can select the city. So one of the 5 case studies. The year for the base case is 2015. And then you have the 2 modes, the base one and the scenario one. In the base one, you have the emissions, so you can select here the pollutants and the source, and then you obtain some maps. For the concentrations, the same thing, the PM10 incidences, the population exposure, the dose, and the viral disease. Here is the some example for Lisbon. So here, selecting, for instance, the concentrations, Lisbon concentrations, you can select here the metric, so the average, the 90 percentile, and here the all year or just like season, like winter or summer, and here the pollutants, just PM, so PM 2.5 or PM 10, and metals also. And then this kind of map will appear with the concentrations. Same problem.
Zoom'da durduralım mı? Ne yapalım?
Okay, so here we can see the concentrations over Lisbon. So here there is a hotspot near the airport, and this is Lisbon city center. So we have the concentrations, and here we have the values for Lisbon municipality and other municipalities because the domain is quite big, so it includes different municipalities. And to estimate the concentrations, we use the Wolfgang modeling system, and then we use this result of the modeling to train neural networks because we need something fast to run inside the tool. And of course, we validated the modeling results with the monitoring stations. Regarding some of the results, so here we can see the difference between what is the ambient concentration and what is the individual exposure. So one thing is ambient concentration, another thing is the individual exposure, because we have to account, for instance, the indoor concentrations. So we can see some differences here, for instance, for PM10. For instance, we have different groups. Children and working adults, for instance, elderly. So, and because, for instance, the elderly are more at home, so the exposure is less, so it's more reduced if you compare with the ambient concentrations. This here is just some results. For instance, the concentration maps. Then we have the population map in this one, and then we can see the population exposure. Regarding the dose, so the deposit dose of PM 2.5 in the respiratory tract. So we have different regions of the respiratory tract, and we have here two different results. The first result here is the different regions of the respiratory, and we can see that in green, more or less 40% of the PM 2.5 go deep in the respiratory tract. So penetrate deep. And another thing that we can see here is the annual dose in micrograms, these points, and we can see that the students are the group of people in Lisbon that accumulate more PM 2.5 in the respiratory tract. So this is the dose. And for the daily, we can see also the results for daily. So this is the dose. This is the hours of the day, and we can see here. So the different colors are different. So here they are the people are sleeping, for instance. Then here they are at school. So different outdoors is green. So and we can see the different flows in micrograms during one day. And we did this for the different groups of the population. Regarding the viral disease, we have different metrics here, but maybe most relevant the years of lost life here, and the deaths. So we estimated more or less 2,000 deaths by year in this one, related with PM 2.5. And we have also for the children the sick days and days of school absenteeism. This is also relevant. So this is for children, and this is the natural mortality. So here you have the number of deaths. we can have these results for the different scenarios or for the different measures that we can test in the tool. What measures we can estimate or we can test in the tool? Well, here we can see the different emissions in Lisbon, and we see that road traffic, commercial and residential combustion, and maritime transport are the main sources. So we decided to include in the tool measures related to these three sectors. So in the tool, you can select, for instance, the measures related to traffic. You can change here the percentage of petrol, diesel, or electric vehicles in Lisbon. And then you can see the results. You can also change the buses. So from diesel to electric or to gas. You can change the technology of the vehicles from Euro 1 to Euro 6. And also the number of cars in circulation in Lisbon and the number of buses in circulation. Related with the residential heating, you can change the different appliances. This is just appliance with burning, so that burns wood. So it is possible to change, for instance, from an open fireplace to a more efficient fireplace, so certified one, for instance. And here you can change the number of cruise ships because, yeah, Lisbon is a tourist city, so we would like to test this. And you can change the time activity, so the time that people stay at home, at school. This is also possible to change in the tool. There are some results for Lisbon. So this is impacts on health, the mortality and the number of days of severe sickness for children. And these red measures, so MU1 to M6 are related with the road traffic. And you can see that we can achieve a reduction of about 10% of the mortality and the sick days related to if you change the vehicles technology. Okay, the replacement of fireplaces is also relevant, but for instance, the ship crews, we cannot see almost nothing. But this is related with the resolution of the model that we use. We use a model with a resolution 1 by 1 kilometer. So to see something here, we need to use a different model. So the conclusions is that the life indexer tool is very useful, and we can go from emissions concentrations for exposure then to those and to the burden of disease. We can test different mitigation measures related to the road traffic, residential burning, and ships for the different case studies. And the results show that for Lisbon, Porto, and Athens, the measures related with the road transport are more relevant, but for instance for Treviso in Italy, Kuopio in Finland, but also to Lisbon and Porto, the residential heating is also relevant, so the burning of wood. There is a paper, if you are interested about the modeling results, the CAMEX results, the neural networks, so there is a publication in open source you can see. And thank you very much. So please visit Avairo. My email is here. Life Indexer project's website where there is the delivery of everything. My Twitter, my CESAM, so my university webpage. And this is Avairo and the campus. And please visit Avairo. Thank you very much.
Thank you for your interest in study and tool. Do we have any question? No? Yes. Thank you. So thanks to all speakers for this session. Now we will have lunchtime. The next session will start at 2 p.m. This is the end of